Okay. So I think we talked about error in the previous segment. So it might be worth perhaps going into a bit more detail about what kind of things to keep a lookout for when especially we are doing computational stuff, right? So
Correct.
we have a table that might give us a first pass. So one important diagnostic habit I think worth keeping is that whenever a numerical answer looks wrong, we should not just think, okay, this is what it is, right? We should perhaps go through this idea that, something might have gone wrong in terms of what we are dealing, right?
Correct.
And usually there are different kinds of things that come up. We'll discuss some of this today, but there will be others also will keep coming as the course comes along. So I think in the previous segment, we already saw this idea of truncation, right?
Correct.
And when does that happen? Basically, whenever you have an algorithm which involves a limit. So as we saw e to the power x, right? But we are then approximating it with some maybe polynomial functions, and somehow we ended up stopping early, right? So perhaps we set the tolerance level too high. Now that is still kind of like solvable. You basically need to adjust the tolerance level, right? Or you run the algorithm longer, and then that can be solved. Another issue that will come up, especially when we are working with continuous time processes, so stochastic processes, but we want to take it to the computer, and so we'll have to discretize it, right? So we'll see again, perhaps some of it later when we are discussing stochastic processes. So then this sort of issues might come up, and then also the answer is fairly straightforward, which is to make the discretization finer, right? So rather than picking like very far apart points, you kind of like choose finer points. The third type of issue is called rounding. And here the cause is that computers cannot represent every real number exactly in binary. And this may seem abstract, but Shorish, can you give a more concrete example of where?
I will give you a demo that will, I think, make you understand much better. Say 0.1 plus say 0.2. I think that should be exactly equal to 0.3. That's what we have been told, right?
Right,
But if this is in R, I think it will happen same in Python also.
right.
It will say, R will say, oh, it's false.
Also, R is saying that 0.1 plus 0.2 is not equal to 0.3. So
No,
all arithmetic that we have learned is like
is
wrong.
all wrong. So this is a real issue actually. And it will happen, supposed to happen in Python also. We will check when we'll do the Python. We'll check if it Python also do the same
Or
kind
rather,
of
we'll make you
problems,
check. We have
or
already checked.
maybe Python is smarter. We don't know. We will check.
Yeah. Yeah, I mean, let's see. Let's see what the students think. But why
Right.
is this happening? I mean, this seems very weird, right? Is all school arithmetic wrong? I somehow don't think so, right?
No, I think what is happening is end of the day in the back in our laptop, the things are coded as binary, right? Every numbers, uh, natural numbers are coded can be coded in binary, but when it comes to decimal, right? So representing a decimal into with a binary is very difficult, right? One third, is it 0.33 or is it 0.333? Because if I stop at 0.33, that means it is 330. It's not anymore 333. But is it 0.3333? Then that means wherever I stop, after that everything is zero. Right? So decimal points are much difficult to represent in binary, and that is without going into much detail of how these numbers are being handled. I think we have to be cognizant that when we are dealing with fractions, dealing with decimal numbers in computer, we have to be very careful, and that is why our algorithms have this kind of uh, uh, we never test for exact equality, but we will test for less than or greater than, because if we go for exact equality, it will always false. You will end up false. Your uh, algorithm will never converge effectively.
I mean, if it was 1 plus 2, we would not have a problem. But we don't know a
Exactly.
priori if it is
Yeah.
1 plus 2. It may be some decimals, and then we may run this
Correct.
issue that they
Correct.
would say,
Correct.
right,
Absolutely. Absolutely.
right,
Absolutely.
right. So I think another important consequence is typically we want to prefer closed forms whenever they are available, right? Rather than
Right.
doing this sort of uh, computing issues, right?
Correct. So if I have this kind of form, I would prefer over e to the power RT, because e is itself is a irrational number. I don't want to work with an irrational number.
Right. So, are there some other issues we need to worry about when we are dealing with numerical quantities? So, are there different types of errors uh, that are
For
there?
example, if you are trying to sum lot of small numbers in different orders, it can give you answer that differ in the last few digit, not maybe fifth digit. Maybe it gives you a little bit of fifth digit or sixth digit differences. But if
Right.
you keep adding up, that means those are actually error. And all those things, when it gets accumulated, it may actually give you a very
Right. Right.
like quite a bit of deviate from the original number.
Right. So, I think all of this follow from the fact of this no exact binary representation.
Exactly. So representing by decimal numbers using binary representation is a real difficult problem in computer science.
Right. Okay. So, but apart from the three that we talked about, this truncation, this discretization, so are there some other things that we also need to worry about? So,
In the rounding error, mostly these are the issues, right?
right. But I think you mentioned something that is, I think, quite new for a student, let's say, maybe in economics, right? Something called ill conditioning.
Yeah, that's a slightly different issue actually. It's not a more like an error issue. It's more like a problems, geometry problems that resulted into a computer science problem or computing problem. So, for example, you are trying to solve like a system of equation. Now, here is you have one system of one equation x minus y equal to 1. Another you have x minus 0.99 y equal to 1.01, right? Now, one solution is definitely x equal to 2y equal to 1. Now, on the right hand side of the second equation, from 1, if you just uh, increase it from 1.01 to 1.02, then effectively it's a 1% change in the input, because now it is basically x minus 0.99y is equal to 1.02. So the only change is from 1.01 to 1.02. Now, if you try to solve, you got x equal to 3 and y equal to 2. You will be able to see that.
Right.
So 1% change in your here, a little bit of change, your x value changes from 2 to 3, which is 50% change, and y value changes from y1 to 2, which is 100% change, right? So two equation describe now why it is happening. If you draw these two equations, they're almost parallel. They're almost parallel. Because of that, it you will your solution they probably meeting sometime somewhere, but that because they are almost parallel, it's this kind of situations are called ill-conditioned problems. Um, and if you get a ill-conditioned problems, then and you are trying to find a solution of the ill-conditioned problems, then it's a real difficult problems actually.
Right, right. So the fact that we use linear equations to describe it probably means that once we get to the linear algebra portion of the course, we'll have more tools to think about this
Yeah,
problem.
linear equation is something we will be using in solving lots of problems, not only in computational finance, in beyond computational finance, also in economics, in sociology, everywhere linear equation comes in. And if these equations are ill-conditioned, means they are very close to being parallel, then not exactly parallel. Remember that. That means if they are not exactly parallel, That means they have a solution and you will get a solution. But question will be, can you trust the solution? Is it a solution based on which you will write your next paper, based on which you will invest your money, or will you invest public money? Because it's a responsibility. It could be somebody's pension fund, right? So we have to be very careful in those cases.
So you mentioned that this was a different kind of piece. So what exactly fundamentally is the difference? I see here you have highlighted this, like, one as like algorithmic stability issues and the other as problem conditioning issues. So what are the differences you would say around it?
So the algorithmic stability is under our control. We can fix it to an extent. It's a small error in the input leads to a small error in the output at each algorithmic step. So you can choose a more stable algorithms, or you decide, okay, I will run it. I will make sure I will run it long enough to get a very stable answer. But if the problem is about conditioning, that means it's not in our control. It is not in the, because effectively I have a parallel system, a parallel lines. It should not have a, if I have a very near two parallel lines and I'm trying to find a solution for that where these two lines are matching, I'm trying to find that. But in this kind of conditions are called ill-conditioned problems. And unfortunately, we have some partial solutions called reach corrections and then lasso corrections. Those kind of corrections are being developed, but I don't think it ever gets really solved.
Right, right. So, but at least we need to be aware of when such things can
100%.
happen. So, diagnosis is important to, I mean, even,
100%.
and probably we'll see that later in the course about how we might be
Yes.
able to do it.
Yes. Yes.
So I think perhaps it's a good time to take a break before we introduce the students to another important finance problem.
Yes.
So let's take a break for a few minutes.
Sure.